the time domain analysis of a first order system, right? A first order system, the generalized form of a first order system is 1 by 1 plus st, where t is the time constant of the system. So how will you define the time constant of a first order system? It is the time taken by the output response to reach the 63.2 percentage of the steady state value, right? Then one more thing we have studied at when small t equal to 3 times the time constant, the output is 95 percentage of the final value. Also for 4t, it is 98 percentage of the final value. So usually in practice, either 95 percentage or 98 percentage of the final value, plus or minus 2 percentage or 5 percentage, is considered as the steady state value. For 5 percentage, time is 3t. For 2 percentage tolerance, it is 40, right? So this, then we have seen that the derivative of step response, it gives impulse response, and also if you take the derivative of ramp, you will get the step response, right? Then we have seen how to find the steady state value of a steady state value of the output response using final value theorem. Okay. Then we have seen one example that one RL circuit with DC excitation, which is similar to that. It is a first order system, and for an RL circuit, the time constant is L by R, means the ratio of inductance value and to the resistance value. So then we have seen that for L equal to 5 millihenry, R equal to 1 ohm, the time constant T1 is equal to 5 millisecond, and if, then it depends upon the system parameters, right? In case of T2, it is 1 millisecond. Then we have found out that systems 2 is faster than system 1. Now, what we can do is we will find the poles for this system, the above said two systems. How can we find the pole? Right. For a first order system, the transfer function is equal to 1 by 1 plus s t. Okay, right. Otherwise, we can write 1 by t divided by s plus 1 by t. Yes, right. So in case of this RL circuit, the pole becomes, we already mentioned that for a first order system, the pole will be a minus 1 by t, right? Okay, now for the case 1, what is T1? T for the case 1, the time constant is 5 millisecond. So what is the corresponding pole? What is the corresponding pole? Is 1 by 5 e power minus 3. So the pole location is at minus 200. Okay. What about the case 2? Case 2, we know the time constant is 1 millisecond, and corresponding pole we can write like this: this minus 1 by 1 e power minus 3, which is equal to minus 1000. So what is the conclusion, or what is the observation from this? Day before yesterday, we have seen that the pole which is closer to the imaginary axis, or the pole which is closer to origin, is dominating the output response, right? We have seen, compared to the far away poles, the pole which is closer to the origin is dominating the output response, right? So if we draw the two systems, means we will draw the pole. This is for case 1. This is for case 2. This is imaginary. This is real. This is So if I locate these poles, for the case 1 it is 200. Let it be somewhere here. This minus 200. This is the origin. Okay. For case 1, it is 1000, right? 1000 means it is far away from 200 and origin, right? Let it be somewhere here. This is 1000. And from yesterday's analysis, we understand that T1 is the slower pole, right? Means what is the time constant of this one? 5 millisecond. It is taking more time to reach the steady state value, but T2 is taking lesser time, right? So that means the pole which is closer to the imaginary axis is having slower response, right? So this pole is having slower response, and this is having faster response. And one more thing, we have already find out that the pole which is closer to imaginary axis is the dominant pole. Dominant pole, right? Why it is dominant pole? Because it is dominating the output response of the system. So compared to faraway pole, it is dominating. Yes, okay. But this see, compared to you compare this value. This is 200. This is 1000. It is very much far away from this pole, right? So we can call this as insignificant pole. Because if you move further towards the left side, that pole has no effect on the output resistance. Sorry, output response of the system. Sometimes you can neglect that poles also, right? So that is the observation. The pole which is closer to the imaginary axis is the dominant pole, and the response of that pole is very slow compared to the pole which is far away from the imaginary axis. And the pole which are located at far, means for that far away poles are called fast poles, because if you move further to the left side, what about the response of that particular pole? Because it will reach the steady state very fastly, right? So that is the conclusion. So we can draw one diagram like this, and we'll conclude it. So in general, I take like this. Let it be real part. This is imaginary part. Suppose I have a pole at this location. It's very closer to the imaginary axis. So this region I can call it as slow or dominant pole region. This is very important to keep in mind. And I will take some other location which is far away from the origin. I can call this as what we can call this fast or insignificant pole region. Insignificant. In other way, what we can tell is, suppose I have a third order system. For example, I have a third order system. Out of that, two poles are for a third order system. Obviously, number of poles will be 3. Out of 3, suppose 2 are very closer to the origin. One is very far away. It is far away from the imaginary axis. But according to our understanding, the pole which is located in the far location is having, it is an insignificant pole, right? even though it is reaching very fast, it is not. It has no effect, less effect on the output. So sometimes we can neglect that pole because it is not affecting the response of the system. So if you neglect it, what will happen? The third order becomes second order. So in such cases, it will be useful for the control system design. Anyway, we will come to that point later. So for our analysis, if you are able to reduce the order, it will be very helpful, right, for the mathematical analysis. Okay, in such case we can eliminate it. Otherwise, we cannot eliminate that one. Okay. Anyway, so that is the conclusion. So the conclusion is the speed of the output response is determined by the slope poles. That is the conclusion. Because slope poles are the dominant poles. Speed of response is determined by the slope poles. Another point we can write: fast poles are ignored, hence they are insignificant poles. So hope everyone understood this concept, slow pole and fast pole, and also, yeah, ask me, ask me. No, what you are asking? All the poles are far away from the origin. Yeah, we can. It can be neglected. So it depends upon the location also compared to the first pole, right? See, yeah, if one is the first pole is at some 200, third pole is at 205, fourth pole is at some 300. Right. First one is compared to other poles. First one is closer to the origin, right? But that pole will decide the output response. So in that case, we can neglect the other two. And suppose S1 is at 1, S2 is at -2, S3 is at some 1000 or something like that. You don't need to worry about S3. Because what about the response? 1 divided by 1000, right? 1 millisecond. What about the other response? Suppose S1 is 1. Your time constant of the S1 is 1 second, right? So you compare it 1 second and 1 millisecond. You see, 1 second means it will take some time to reach the steady state response. But the faraway pole is reaching the steady state very fast. And another observation is that the pole which is taking 1 second to reach the steady state is the dominant pole. So in that case, you can eliminate the other pole. Nothing will happen. So while designing a closed loop control system, because anyway, we'll come to that point. Again, one more component will come into the picture, right? Let it be controller. So controller also has some other transfer function. It will increase the order of the system. So if you are able to cancel some pole, but this won't be good for all cases. This pole zero cancellation. Yesterday I told one concept of pole zero cancellation also. Anyway, we'll come to that point later. Hope you understand the concept clearly. Okay. So today we will do some numerical problems so that you can understand more. And one more thing is I want to tell is delay, process delay. Means for time delay, we can call it as time delay also. time delay in the sense sometimes from one component to other component, there will be some processing delay in practical case. Okay, in that case, suppose the delay time is delta, we can the corresponding transfer function of that delay is e power minus delta s. So if you have a system function here e power minus 2s, it means that the delay time is 2 seconds. This also you keep in mind. Anyway, process delay also we will see in the detail, because why I told you is in our problem sometimes they will give this delay function also. At that time, how can we draw the response, everything we will see today. Okay. So we will move to some questions or note down this question. You also work out. I hope everyone have a notebook with you. And one more thing I want to ask, whether you are simply watching or you are also practicing, because you are practicing, right? You while you can using this, you can also write on your book. Because practicing is very important. And then only you can do the analysis problems, everything. Okay. So please note down this transfer function. Is 10 divided by s plus 2. The question is, sketch the response for two cases when input is equal to 2 times e of t, and the second is when input is u of t minus 3. Okay, so we have a first order system. The question is, we have to plot the response for two inputs. Both are step input, right? Both are step input. So if you consider the first case, our input is 2 u of t, right? So how can we draw the input signal? It is not a unit step input, it is a step input with magnitude 2. And I draw like this, right? And what about the second case? How will you draw an input u of t minus 3? This concept you might have studied all those things in the signal sense system. What is t minus 3?
Time delay.
Yeah, it is a time delayed function, right? So here, yeah, here it started at time t equal to 0, but for the second case, so the input waveform look like this. What is the magnitude of this? It is 1, right, with time 3. So this is the delay. So now see how can we draw the output response. So in both cases we understood that the input is step function, right? So what is the Laplace transform of 2u of t?
2 by s.
2 by s. 2 by s, clear. What is the Laplace transform of u of t minus 3? This 1 by s only. Then how this 3, this delayed time function, will impact on the output response? That we will see. Okay. So that what we have to find it. So in order to plot the graph, we need to know the steady state value, right? Since it is a first order system, it will, the response will start some point and it will increase exponentially and settle at some value. Right? That is the nature of the first order system. And in our system, we know what is the time constant of the system. So in this case, what is the time constant of the system? T is equal to 1 by 2, because it is in S plus form, right? So it is 0.5 seconds. For the given problem, that uh, the time constant of the system is 0.5 second. So in first case, how will you find out the steady state value? So in order to find the steady state value, you have to apply the final value theorem. That is C of infinity equal to limit s tends to 0, s multiplied by y of s. Right, this is the equation. So using that, you can find out limit s tends to 0, s multiplied by y of s is nothing but 10 divided by s plus 2 multiplied by input. Input is 2 by s. So this s and s can be cancelled. So we can get 10 divided by 2 multiplied by 2. So 2 got cancelled. So the steady state value is 10. You know the steady state value. So how can you draw the output response? Since the input starts from origin, this also will start from origin. Since it is a first order system, it will exponentially increase and finally it will reach the steady state. Sorry, the steady state value is what? 10, right? Anyway, I will redraw it. Let me draw here. P of t, P of t equal to. This will be the response of the system with the steady state value 10. Clear? So for case 2, how can we find out? For case 2, we can find the steady state value y of t is equal to limit s tends to 0, s multiplied by 10 by s plus 2 multiplied by 1 by s. S and s got cancelled. So you will get 10 by 2 is equal to 5. So how to draw the wave? See, it is a delayed function. It is a delayed function. If you take x-axis t, y of t, whether it will start from 0. It will not start at 0,
No,
right?
sir.
Yeah. The waveform will start at time t equal to 3 seconds. Then it will slowly increase, and finally it will reach the steady state value, and that value is 5. Clear? So this will be the difference. Clear? Yeah. So if we take another problem, I have a transfer function Tf is equal to 10 e power minus 2s divided by s plus 2 s plus 5. And fits the response of the system. How will you draw it? So in this given problem, you can observe that there is a delay function, that is e power minus 2s. So this is a delay function with delay time 2 seconds. Okay. So you have to find the sketch response of the system for these inputs. The first one is 3 v of t. The second one is 4 u of t minus 6. So how will you plot this? First of all, we want to find the steady state value, right? So we can find the steady state value by applying final value theorem. That will limit s tends to 0, s into y of s. Y of s is nothing but 10 e power minus 2s divided by s plus 2 s plus 5 multiplied by Laplace transform of input, right? With 3 ut is 3 becomes 3 by this and this got cancelled. So what will be the answer? 10 e power 0 3 2 into so will be 3. So how can you draw the waveform? So what is the impact of this delay function in the output response? Since a delay function is there, it will not start at 0. That is the condition. So it will start at that delay time. What is the delay time of the function? It is 2 seconds. So it will start from 2 and finally it will start with a steady state value. Clear? So how will you draw for the second case? Again, you want to find the steady state value. So it will become limit s tends to 0, s multiplied by the planned model is 10 power e power minus 2s divided by s plus 2, s plus 5. What is the Laplace transform of 4 u t minus 6? And here also it is a delayed time function with a delay time of 6, right? So we can, if you take the Laplace transform, it will become 4 by s. So s and s will cancel. What is the steady state value? 4, right? 10 got cancelled. So now, how will you draw the waveform? So in this problem, already the plant is having a delay. What is the time delay? 2 seconds. Again, you are feeding a step signal with the delay time of 6. So what is the total delay? Is
8 seconds.
8 seconds. 8 seconds. So it has to start from 8 seconds and slowly it will increase. It will settle at some point. So what is the magnitude? Clear?
Yes, sir.
Okay. So now what you can do is given the planned model is A divided by S plus A. Okay. And also you have given that the time taken by the step response to reach 95% of the steady state value is 6 seconds. So still find the value of it. How will you find? Given a transfer function having a divided by s plus a, we don't know what is a, it is a real number. And given information is for this system, in order to reach the 95% of the steady state value is taking 6 seconds. That is the hint. So for 5% tolerance, plus or minus 5% tolerance, what is the time?
3 time constants.
Yeah, 3 times time constant of the system. And this is given as 6 seconds. So what is t? T is 6 by 3 become 2 seconds. So this will be the time constant of the system. So from transfer function, we can rearrange it. A divided by, if you take A out, it will becomes 1 plus S by A. A will cancel. So if you compare with standard transfer function 1 plus st, on comparing these two, you can get t is equal to 1 by a. So from this you can find a equal to 1 by 2 is equal to 0. So your system becomes, so your actual system is 0.5 divided by s plus 1. Whole is at s equal to minus 0.5. Clear? So you can, yeah, you can expect this kind of questions in the GATE exam. Okay. So you most probably will write in next year or fourth year. You will attend, right? So you have to practice a lot of problems. So you can expect this kind of problems. Okay. Then you will solve some of this. Your block diagram has given that this is input, this is plus, and this is the k divided by 1 plus st, and there is an output. Let's say feedback loop in the system. So this is the system, and also given that the response of the system is like this. So these are given without response. Actually, find okay. Is it okay now? Presentation. What about presentation? Okay. Is it okay now? Fine.
Yes, sir.
Okay. Okay. So, so this so a system block diagram is given and the corresponding output is also given. Question is find the value here. So how will you find it? This is a closed loop system, right? The given system is a closed loop system with gain 1. So it is a unity feedback, unity negative feedback system. Right? So how will you find the transfer function? Yeah. So in this case, g of s is k divided by 1 plus st divided by 1 plus k by plus st. To solve this, you get k divided by plus st plus k. Output response as given, right? In this, we know only one parameter. What it is? It is the steady state value, and the steady state value is given as 0.5. So that what we can do is we can find out the steady state value using final value theorem. So we can write limit s tends to 0 s by 1 plus st plus k. The response you can understand that unit step response, right? So corresponding input is unit step input. We can cancel it. We get what is the value of the k divided by 1 plus st. So not st, 1 plus k divided by 1 plus k. And it is given as 0.8. So if you solve this, you can find out k. Right? K divided by 1 plus k to the 0.8. If you solve this, you can get k as 4. This will be the answer. Clear?
Yes, sir.
You can take it as a step in. Actually, since the magnitude is 0.8, you are you got doubt, right, whether it is unit step input or some other magnitude. So you can take the input as step input. Yeah, generally you can do it. This is the output response we are comparing. To take input task, what is the input? So 1 by s here. So s is will cancel. Finally, you will get the steady state value in terms of a. And from the response, it is understood that the steady state value is 0.8. So if you get these two, you can get a as well. Clear? Do we have class in the next hour? Okay, 5 more minutes. Monday. So that's the thing for a customer system. So we sounded. Okay, we'll wind up today's class. We will start continue on Monday.